When we were a kid, we were all wondering how cars on the street can move and what their engines look like. And it turns out to be for most automobiles that consume gasoline as the power source. Those automobiles' engine is designed based on so-called Otto Cycle in thermodynamics. So today we are going to take a look at Otto Cycle and see how those engines work. All right, then this is a typical illustration for a petrol engine. So we usually call it as a 4-stroke cycle engine. It's like a piston cylinder system and has 4 strokes. So we call it as 4 strokes, and actually it has 6 processes. So it's starting from a 1, so 1, then 2, then 3, and 4. But we actually have 6 processes from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 back to 1, and 1 back to 0. Then since from 0 to 1 and 1 back to 0, it's just an isobaric process. So we don't do a lot of analysis on that. So when we take analysis for Otto Cycle, we usually take a look at 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. So before we move forward, let's take a look at a definition, compression ratio first. So in order to understand the compression ratio, we are going to define a top dead center and a bottom dead center. So the top dead center means when the piston is at the top, then we have the minimum volume in the cylinder. And as the opposite, the bottom dead center is defined as when the piston is at the bottom, then we are going to have the maximum volume in the cylinder. So the ratio of Vmax, which is the maximum volume, over the minimum volume, we define this ratio as compression ratio. Then we are going to use this ratio in the future. So let's take a look at all those 6 processes again. So from 0 to 1, it's an isobaric process. So the pressure doesn't change. So it's air intake. So air will get in here. Then the piston will move downward. The next one is 1 to 2. Looks like the volume decreases and the pressure increases, and we call it as compression. So the piston will move up from the bottom to the top. So the air, they are compressed. The next one is 2 to 3. It's an isochoric process, means the volume does not change. So since the volume does not change, means the piston is at the top dead end. It's happening instantly. And we call this process as ignition. From 3 to 4, the piston starts moving down, and this is a power process. So from 3 to 4, it generates power. And the next one from 4 to 1, it's another isochoric process. So the volume does not change, means it's happening instantly as well when the piston at the very bottom. And it's a heat rejection process. Then the last one is from 1 to 0, then it's exhaust. Then the air goes out. And still for Otto cycle, the PV diagram, P is pressure, V is volume. Then like we said, we only analyze the 4 processes, 1 to 2, 2 to 3, 3 to 4, 4 back to 1. Then turns out to be from 1 to 2 and 3 to 4, they are both isentropic process. And in the previous lecture, we have learned isentropic means adiabatic plus reversible. So if the process is an isentropic process, then that will cover all the characteristics of adiabatic process. So which means from 1 to 2 and 3 to 4, since it's adiabatic process, then we won't have any heat transfer. And from 2 to 3 and 4 to 1, they are isochoric processes. Means the volume does not change. Since we won't have any volume change, then from thermodynamic work is defined as the integral of PdV. Then since we don't have a volume change, then we won't have any work from 2 to 3 and neither 4 to 1. Then we could also plot the TS chart. T is temperature, S is entropy. Then like we said, from 1 to 2 and 3 to 4, they are isentropic process, means entropy does not change. Then as you can see on the diagram, 1 to 2, we have the same entropy, and 3 to 4, it has a constant entropy as well. Then 2 to 3, the temperature increases. And from 4 to 1, the pressure decreases. Still this chart, then the PV chart. This is also the one we are going to take calculation examples. Then from 1 to 2 and 3 to 4, they are isentropic processes. And since the media is air, because for petrol engine, we have only 1 drop of gasoline at a time. So all the rest, they are air. So the media in Otto cycle, they are air. So you can look up the thermodynamic table, then turns out to be for air, the constant is 1.4. Then from 2 to 3, it's heat in. And from 4 to 1, it's heat out. And at state 3, it has both the maximum pressure and also the maximum temperature. Then let's think about the work. Then from 1 to 2, volume decreases, so we expect a negative work. From 2 to 3, no volume change, so no work. From 3 to 4, the volume increases, so we expect a positive work. From 4 to 1, no volume change, so no work. Then let's think about the overall work. Since the cycle is running in a clockwise one, so we expect a positive overall work. Now let's look at the efficiency. So efficiency is defined as what we want divided by what we pay for. And for Otto cycle, what we want is definitely work out. So we want the engine to generate work for us. So we are looking for the work of the entire cycle. So 3 to 4, we have work out, but 1 to 2, we have work in. So we need to look into the overall work of the whole cycle. So that's why it's the work for the cycle. And for what we pay for is heat in. And in Otto Cycle, heat in is from 2 to 3. And this is the efficiency for Otto in a diesel cycle. It's the work of the entire cycle divided by heat from 2 to 3. Then in the next class, we are going to look at an example, and we are going to use all those formulas. And if you're not familiar with them, please study on your own first. All right, then this is all we have for today's part. Thanks for watching. We'll see you next time. Bye.